So let's look at section 1.1 for the book Probabilistic Methods. So probabilistic methods is a really powerful tool to tackle many problems in discrete mathematics. So oftentimes you'll be asked to show that certain objects or mathematical objects exist. So instead of explicitly construct this object, what you can do is you can define a probabilistic space over a collection of mathematical objects, and then you show that the probability a certain property will happen will be strictly positive. A really famous example, whenever people talk about probabilistic methods, has something to do with the Ramsey number. So Ramsey number, RKL, is defined to be the following. So RKL is the smallest integer n, such that if we color the edges of a complete graph with n vertices, and for each edge you either color them by red or blue, then you know there always exists a red complete subgraph with k vertices or a blue complete subgraph with l vertices. And quickly, let me define what is a complete graph. So a complete graph with n vertices is a graph where all pairs of vertices are joined by an edge. So for instance, this is a complete graph with 4 vertices. So now let's see how we can use probabilistic methods to provide a lower bound on Ramsey numbers. So here's the proposition. So what this proposition is telling you is that the Ramsey number grows exponentially in the parameter for the Ramsey function. So in order to show that this proposition is true, let's read the proposition in a slightly different way. So in order to show that Ramsey number is strictly greater than this quantity here, it is enough to show that there is a way to color a complete graph with exactly this number of vertices, such that for this particular graph, there's no blue complete graph with k vertices, and there's also not a red complete subgraph with k vertices. So essentially, we kind of convert the Ramsey number kind of problem into an existent type of problem, and now we can use the probabilistic method. Now for the proof, let's define a probabilistic space, and also let's define a certain event. So we let AR denote the event, such that the induced subgraph of the complete graph on the vertex set R is monochromatic, which means all the vertices have the same color. And this R, as mentioned, is a subset of all the vertices of the complete graph. So one can easily write down the probability of this event, which is this. Okay, so here the numerator is 2 because there are 2 ways to have a monochromatic triangles. So you can have either a red one or a blue one. And the denominator is just the number of ways to color this complete subgraph. So now let's use this event to write down the probability that there's not a blue kk nor a red kk. So that is the probability that there do not exist a subset of the vertices with size exactly equal to k, such that this event AR is true. So if such R does not exist, and then you know in this graph you don't have a blue kk nor a red kk. And your goal is to show that this is strictly greater than 0. So we can write this probability as 1 minus the event complement. And further, this event complement can be written as a union of many smaller events. And then one can use the union bound to bound this probability. In particular, this is greater than or equal to 1 minus the sum of all these probabilities of the smaller events. And now we can kind of plug in this quantity we calculated earlier, and to get this equal to this. And this number n choose k is just the total number of ways you can have this subset R. So now we just want to show that this quantity is greater than 0, Or in other words, we would like to show that this quantity is strictly less than 1. So now let's open up this n choose k and k choose 2. And we can see that this quantity is less than or equal to n to the k power divided by k factorial multiplied with 2 to the 1 plus k over 2 divided by 2 to the k squared divided by 2. Next, let's rearrange the terms here and also plug in the value of n. And we further get this quantity is less than or equal to 2 to the k squared divided by 2 divided by 2 to the k squared divided by 2, where this numerator we get by plugging in the value here, and the denominator we get just by moving this to the denominator here. And now we have the leftover terms, which is the following. And now we can see that this first part exactly equals to 1, and the second part is strictly less to 1 because we assume that k is strictly greater than 3. So all in all, we show that this is less than 1. And if we backtrack, now we show this. We know this quantity is strictly greater than 0. And this is exactly what we want to show in the beginning. So that's the end of the proof.